check where we left off. I think we had left off at approximately buffers starting, right? So we had discussed for weak acid, weak base kind of salt. So let me just quickly give a recap of the formula there. So if I have a weak acid, weak base salt, like say CH3CO minus NH4 plus, this fellow is an ionic system which will dissociate completely to become CH3CO minus ions and NH4 plus ions. So this would have been C, 0, 0, this will become 0, this will become C and C. So in the solution we are going to be having conjugate base and conjugate acid. Both of these are stronger than water respectively as base and acid, so they will react with each other. So the formula which we are going to be getting over here, I'll just quickly discuss the formula here. This is an important formula which you need to make sure that you are memorizing. This is one of those bunch over there. So I would say this is like the fifth formula you will definitely have to memorize perfectly. So pH of the solution of salt of weak acid, weak base, where concentration is C, concentration is C. This is critical. Works out as half into pKa. What did we get? I forgot the damn formula finally. It's simpler to derive it and go for it, but yeah, as I said, this is an important formula to be memorized properly. pKa plus pKw plus pKa minus pKb. Okay. So we are going to be having it as half into pKw plus pKa minus pKb. So pKw plus pKa minus pKb. In this case, this is for the weak acid, this is for the weak base. Now this is a formula which you have to memorize. There is no escapism for this formula. Ideally speaking, I should also have memorized the damn formula, but yeah, laziness and just going through this formula once in the previous day and a slightly related formula basically kicked this out of my brain, I suppose. I'll remember it definitely as well. So half into pKw plus pKa minus pKb is going to be the formula associated over here. This formula is very powerful in the sense this is something which you can use when concentration of weak acid or conjugate acid is equal to concentration of weak base or conjugate base. As long as they are both in equal concentration, you are going to be having this formula straight away being applicable. You don't need to think about it beyond that. So the next piece we had discussed was NaHCO3, any solution, any concentration basically. So if I am having only NaHCO3, this fellow will break into Na plus and HCO3 minus. Na plus is spectator anyway, so we don't need to care about it so much. This HCO3 minus is both the conjugate base of Ka1 and it is going to be the weak acid Ka2. So when you are having it in this fashion over here, directly we can now proceed and say, since this is the only fellow which is present, if this was concentration C, this would have become 0, 0, 0, C and C. So my HCO3 minus is the only thing which is going to be mattering over here, and that fellow's concentration is C, and that is both the conjugate base and the weak acid part over here, meaning I can apply the equation pH equal to half into pKw plus pKa, which is pKa2, minus pKb of what? Of the conjugate base Ka1, meaning this will work out as half into pKa1 plus pKa2. The pKw gets cancelled, we end up having this as the pH of the solution finally. So in a similar way, any middle salt you are going to be taking, say H4A, after Ka1 this will become H3A minus, after Ka2 this will become H2A minus 2, after Ka3 this will become HA minus 3 or HA3 minus, and after Ka4 this will become A4 minus. So if I am looking at the pH of each of these middle fellows over here, so if I am interested in pH of this will be half into pKa1 plus pKa2, the previous and the next, and this fellow's pH will effectively be half into pKa2 plus pKa3, the previous and the next. And the next one over here is going to be this fellow over here, HA3 minus. This is going to be half into pKa3 plus pKa4. This one and this one. So we're going to be having it in a very straightforward manner like this, and we can proceed on and understand how it's supposed to work. Now let's talk about buffers and define what is meant by a buffer solution. Then we'll come back to what we have discussed a little bit so that we'll connect the pieces up. So when we are looking at a buffer solution, it is going to be something which resists the change in pH. This is what is meant by a buffer solution. Meaning it is going to be, for whatever reason, however, it is going to be resisting the change in pH when small amount of strong acid or strong base is added. This is the worst kind of condition. So when a small amount of strong acid or okay, it's got DC, so I can wait for a bit. System is okay there? No problems?
Yes, sir. Just some internet issues.
Okay. So we'll continue on. So buffer solution is going to be resisting the change in pH when, under all conditions actually, but mainly when you're going to be having a small amount of strong acid or a small amount of strong base added to it, because this is going to be the worst possible condition. Of course, dilution also. Okay. That is, when you're adding water also, pH should not be changing so much. It should be approximately the same. Now let's try to understand what is the way this can work out. So dilution, we have already seen. What does dilution case mean? It means does not depend on concentration C. On C. Or C adjusts mathematically. Or C gets adjusted mathematically. So that is the basic idea over here. So let's neglect that part for the time being. We'll come to the other bit over here, which is more complicated. So when a small amount of a strong acid or a strong base is added, what is going to be happening? Say for instance, if I was going to be having 999 ml of pure water, and I added say 1 ml or 1 drop of 1 molar HCl. What happens over there? Originally the pH should have been 7. Finally, what becomes the pH over here? The pH becomes, on adding this 1 ml over here, you will end up having H plus concentration equal to 10 power minus 3. Because 1 ml, 1 molar, so 1 millimole. 1 millimole is in 1000 ml, so 10 power minus 3 molar, meaning pH works out as 3. So normally when you are going to be having a solution, which is going to be like pure water type of thing, when you add 1 drop of a strong acid or a strong base, the pH will change ridiculously. If I added the base over here 1 drop, same concentration, I'll have pH becoming 11 from 7. So the pH will change abruptly when you're adding a tiny bit of a strong acid or a tiny bit of a strong base to a solution normally. So let's now try to understand how something can resist the change in pH over here. If I have a strong acid added, if the strong acid gets neutralized, say for instance, if I had a base present in solution, alright, NaOH is present in large excess. In that particular case, I am going to be having a reasonable amount of HCl. As long as I am adding, pH is not going to be changing by much, because the NaOH which is left over will decide the pH. So if strong acid gets neutralized by solution completely, then pH doesn't change by much. So what can neutralize a strong acid over here? So a strong acid can be neutralized either by a strong base or a weak base. These are the two things which can neutralize a strong acid. Same way, if I am going to be having a solution which is going to be resisting change of strong base over here, same principle in opposite reply I would say is applicable there. If strong base gets neutralized, by solution completely, then pH does not change by much again. So in this particular case here, what is going to be capable of neutralizing this fellow over here? You will have either a strong acid which can neutralize a strong base or a weak acid. Both of them are capable of neutralizing the strong base added in over here. So when you're going to be looking at a solution which is going to be doing both at the same time, alright, so both strong acid which is getting neutralized by either a strong base or a weak base, and strong base which is going to be getting neutralized by either a strong acid or a weak acid. So solution should resist both pH changes. Solution should resist both. That means this kind of a solution should contain one of these green colored fellows over here and one of this pink colored fellows over here. One of these two is necessarily needed to be present over there. Each basically. So buffer solution, if we are trying to understand what that is, it should resist the change in pH for sure. So if it should resist the change in pH, one of these two should be there, one of these two should be there. So it can be 4 possible combinations: strong base plus strong acid combo, or strong base plus weak acid combo, or weak base plus strong acid combo, or weak base plus weak acid combo. These are the 4 possible combinations which are going to be technically feasible, mathematically at least, to be a buffer. But there's problems here. The problem here is this. Let's take the strong acid and strong base combination. This one here, they neutralize, they react with each other. If you mix the two of them, they react with each other till full completion. Meaning one of them is consumed. Either the strong base will be consumed or the strong acid is consumed. One of them is consumed. If one of them is consumed, then pH will be changing weirdly at certain conditions when you are not having both of them in similar quantities. They can't exist with each other. So both of them are going to be nullifying each other completely, or one of them is going to be nullified completely, which means this solution is not technically possible. Same way here, when I am considering strong base plus weak acid, the strong base will react till its full completion or till the weak acid is fully completed, because it is a strong base. So this will also react with each other to full completion, definitely in this case also. Same thing applies to the weak base plus strong acid condition here as well. This will also react with each other till full completion. The last case is the real viable case, which we are going to be now considering. So what is this last case over here? Weak base plus weak acid. Let us try to understand what happens when you are mixing a weak base plus weak acid. So this is going to be the only viable case. So let us try to see what this really stands for. What does this really mean? So if I have a weak acid reacting with a weak base, what will I have? I will have this not necessarily going to full completion. There will be an equilibrium absolutely present over here. The weak acid will effectively become conjugate base of weak acid, and the weak base will become conjugate acid of weak base. Now we have seen a couple of cases. Usually what happens, this fellow's Kb value will be less than 10 power minus 3, and this fellow's Ka value will be less than 10 power minus 3, which means both of these technically are perfectly acceptable as a weak base substitute or as a weak acid substitute, meaning this conjugate base of weak acid is similar to a weak base, whereas the conjugate acid of weak base, this fellow, is going to be similar to a weak acid. In a sense, if I am adding say some strong base to it, what will happen? I will have this acid neutralizing it or this acid neutralizing it, if either of them is present, because both of them are going to be present at equilibrium. So whichever is stronger among the two will neutralize it. If a strong base is added, these two, one of them will neutralize. If a strong acid is added, the two parts which can behave like a base, one of them will neutralize it. So it will be either the weak base or the system similar to the weak base. Whichever is stronger will neutralize the system. That is the idea there. So you have to now compare this guy and find out which Kb out of these two is higher. That will react with the strong acid added first. Similarly, between these two over here, when you are adding a strong base, whichever is going to be having a higher Ka value, that will react with the strong base first and will neutralize the strong base in that particular case. So this is effectively the idea behind a buffer here. So all buffers, so you can think of it like this, all buffer solutions should contain something which is a weak acid or similar to weak acid plus weak base or similar to weak base. It has to be a combination of technically something which is a weak acid and a weak base. Only these kind of combinations will end up being capable of behaving as buffer solutions. So now let us try to break this down into different possible cases and see what are the different types of buffers applicable. So when you're going to be having different types of buffer solutions, the first type of buffer solution is where it is a separate weak acid and a separate weak base. Alright, completely individual different weak acid and a weak base, meaning say something like a solution of acetic acid and ammonium hydroxide. This will be a buffer solution. Now this solution here, you cannot find the pH that easily. It is very difficult to find the pH of a solution like this, especially when the values are given differently. If you are given same concentration, then you can apply the formula half into pKw plus pKa minus pKb and sort it out. If they are not of same concentration, it is still a buffer, but finding pH becomes very difficult. In the same way here, if this solution works, the same type of thing in its opposite way, we can also have salt of weak acid, weak base, like say CH3COO minus NH4 plus. What will this produce? This will produce CH3COO minus plus NH4 plus. Both of them will be 0, 0 in the beginning. This should have been C in the beginning. C in the beginning becomes 0, 0, 0 in the beginning. This will become C and C. So again we are having both of them present in the solution and in equal concentration, hence we will apply over here. But any general salt of weak acid, weak base technically will behave as a buffer. In our domain, we are able to only calculate for this case meaningfully. For all other cases, it becomes much more complicated and much more irritating, mathematically speaking. Big calculations, you'll have two variables, two quadratics, solving will become painful. Minimum, actually 3 variables and maybe 3 equations, maybe not quadratic. I'll have to check what the solving is like, it doesn't matter though, it is not needed in our level. So this is going to be this particular type of case. Next case is going to be, this is effectively, what was this case? Different type of, different weak acid and weak base. That is this case over here. I'm going to call this as case number 1. Case number 2, we are going to be studying is going to be a weak acid and something which is going to be related to it. Related weak base, which is going to be nothing but conjugate base of weak acid. Related, it is going to be conjugate of it. So this is going to be a case where we are going to be considering something like weak acid plus conjugate base of weak acid in same solution. Or it can of course be a weak base plus conjugate acid of weak base in same solution. Now, in your school, when you are learning it, you will probably learn it as 2 different pieces, but they are actually the same. In reality, if you look at it from this perspective, if I consider say CH3COH and CH3CO minus, so technically look at it like this. This is a weak acid, this is conjugate base of weak acid. But if I consider this fellow as something similar to a weak base, then this fellow will automatically end up having CH3COOH becoming conjugate acid of weak base. So effectively, technically speaking, both of these are not different cases. That is, these two are not different cases, they are one and the same. But we will derive two different formulas and then we'll discuss how they are connected to each other so that you have perfect mathematical clarity that they are actually the same. And there is also one more substitute type of definition which sometimes is used in some books. I am not saying all books. Some books where subject is relatively weaker, they will call this first type as acidic buffer and the second type as basic buffer. But in reality, acidic buffer, what does it really mean? Acidic buffer means buffer solution with pH less than 7. That is what acidic buffer means. Buffer solution with pH less than 7. This is going to be an acidic buffer. But sometimes books give it wrongly. This definition of saying this is acidic buffer, this is basic buffer, that is not correct. Because ultimately both are the same. Both are the same. So buffer solution, which is going to be related type, will automatically be the same. For instance, let's say I am taking NH4 plus and NH3. If I consider this as my weak acid, this becomes conjugate base of NH4 plus. Or if I consider this as my weak base, this will become conjugate acid of ammonia. Technically both are the same. If the solution is going to be the same, both are technically representatively the same, both mathematical models should work the same way. They do give the same result, they do work the same way actually. It is just that sometimes certain books, I think NCERT might give it like this, I am not 100% sure, that is why I am mentioning this. This is not correct. Alright, even if it is given in a main setting, this is not correct. If this is given, pick this as the correct answer if it is given in a main setting. If this is not given, then NCERT, remember that nonsense, might be giving it like this. I don't remember it perfectly, but I remember one standard book giving this kind of a definition. One famous coaching book or some standard book which is used in places, standard material or whatever. Correct definition is acidic buffer is going to be a buffer solution with pH less than 7. Basic buffer means buffer solution with pH greater than 7. Okay. Now let's say one of these cases and finish the discussion of it and close it off. So let's say I am going to be having a solution containing, say, CH3COOH at concentration C1. I am just going to call this as weak acid concentration in whatever expression I am going to be putting, and CH3COO minus Na plus salt as concentration C2. Let's call this salt. Or I will be using the other term conjugate base. I prefer using the term conjugate base in this particular case mainly because there will be no mistakes. I explain why I said there will be a possible mistake. Usually in books they will use salt, but I would prefer you to use conjugate base in this as much as possible. And over here, of course, prefer to use weak acid. So what happens over here, the CH3COO minus Na plus salt will basically dissociate completely to give me CH3COO minus plus Na plus. This should have been C2 concentration in the beginning, this will become 0, this should have been 0, 0, this will become C2, C2. This of course is going to be spectator, meaning I don't care. It doesn't affect the pH, we don't need to bother about it. So only actual substance in the mixture. Mixture contains what over here? The mixture in this case contains CH3COOH at concentration C1 and CH3COO minus at concentration C2, and we also have water. Water will of course be part of any equilibrium play over here. So this is what is present in the solution. So let's now try to understand what is the equilibrium which we can play with over here. So we will have weak acid CH3COOH over here having its own dissociation constant with CH3COO minus and H plus. This will be its own equilibrium with the equilibrium constant being Ka in this particular case here. Only problem or difference here is this is having concentration C1 in the beginning, this is having concentration C2 in the beginning, and the H plus is an unknown. And the H plus is an unknown. So let's just leave it as an unknown for now. Okay, so what is going to be happening here? We will have a little bit of this dissociating, the weak acid will dissociate tiny bit. So C1 minus X, this will be C2 plus X, this will be X. Only problem here is this particular value X is going to be very small. Why is it going to be very small? Now we can of course write it slightly differently also. I can write as C1 into 1 minus alpha. I can write this as C2 plus C1 alpha. I can write this as C1 alpha, in which case the X is actually going to be nothing but C1 alpha. But no meaning in putting it like that, it doesn't make a difference over here. So basically X is very small. You can also think of it as alpha is extremely tiny here. So X is very small, so negligible. Compared to what? Compared to C1 and C2. Meaning I can now approximate these two pieces. This and this I can now approximate. And write this as C1, and this fellow also on approximation will end up becoming C2. This on the other hand, I just leave it as a blank over here as an X. We don't know this value, so we'll just leave it as a blank, it doesn't matter. So effectively what do I have as my expression now? My Ka can be written as products by reactants, meaning that is going to be CH3COO minus into H plus by CH3COOH, which works out as C2 into H plus by C1. Meaning we will now be having H plus concentration being equal to Ka into C1 by C2. This is what we end up getting H plus concentration as. So let me put it down over here in full form. So H plus concentration is Ka into C1 by C2. Correct? So we had C1 by C2 over here. C1 is what? C1 is concentration of the weak acid. C2 is the salt or the conjugate base over here. So Ka into weak acid concentration divided by conjugate base concentration or salt. So now if I am going to be looking at pH, pH of course is minus log of H plus. This works out simply very easily as minus log of Ka, which works out as pKa, minus log of weak acid by conjugate base, which can of course be written as pKa. So pH over here of what type of buffer? Any buffer actually, but for now we discussed weak acid plus conjugate base buffer was working out as pKa plus log of, we end up having conjugate base by weak acid. In books you will also find it as salt by acid. Avoid using salt. I will explain that in a bit now in the immediate next page, but avoid using salt as much as you can. So why do I say avoid using salt? Mainly because if let's say I am going to be having something like this. If my salt is going to be say barium acetate and acid is CH3COH. Let's say this is given as C1, this is given as C2. The pH for this solution should be equal to pKa plus log of, it should not be C2 though, it should be 2 times C2 because my CH3CO minus is the operative thing, not the full salt. So it will be log of 2 times C2 by C1, not C2 by C1. So this is where mistakes will happen if you end up taking it as salt. Sometimes when you are in a rush, this kind of a small rushed mistake will happen. To avoid that mistake in the beginning itself, try to remember it as conjugate base instead of salt. How have they discussed it in school for you? You've done this topic before, huh?
Yes, sir.
You remember it as salt by acid or you remember it as conjugate base by weak acid in your system?
I don't exactly remember it, sir.
That makes more sense. Ionic equilibrium is a very forgettable chapter, especially if you are sitting and remembering equations. In this case, you don't need to remember the equation really. If you wish to remember, If you think your memory is comfortable enough, I would recommend you remembering this one. Of course, you can change the equation, adjust it according to the next stage over here. You can convert it directly if you wish to convert it. I'll show you the conversion as well. POH. I'll just put them down over here. So POH for weak base plus conjugate acid. If we are just blindly converting it, it will be, in this case what we have, we had pKa, now it will be pKb plus log of, again in that case it was conjugate base by weak acid, here it will be conjugate acid by weak base, if I am doing a blind conversion. Now if we are not doing a blind conversion, if we are sitting and doing the derivation itself, let's quickly look at the derivation for this here. Derivation is going to be same way. You are having ammonia and ammonium chloride. So ammonium chloride, let's say C2, ammonia, let's say C1. Then we'll end up having equilibrium being NH3 plus, or the NH3 is going to be in equilibrium with NH4 plus OH minus. Of course water is present, but we are neglecting that fellow here. This will be Kb. This would have been C1, this will be C2, this is the unknown. Alpha, or degree of dissociation, is very tiny, so we neglect that. So we'll end up having in this particular case here OH minus concentration working out directly as what here, it will be Kb multiplied by C1 divided by C2, which means from here we will be getting POH being equal to pKb plus log of C2 by C1. C2 by C1 is of course going to be nothing but this equation actually. So you'll end up getting this equation directly. Now let's see why these two are this equation. I told you both buffers are actually the same mathematically. So both equations should actually be giving me the same result mathematically speaking. So let's try to see how that works out over here. Let me put down both equations, or we'll take one of them and derive the next one from that. So let's say POH of weak base plus conjugate acid is working out as pKb plus log of, in this case we had conjugate acid by weak base concentration, correct? So now let's try to play around with this and see how this works out over here. So the idea here is, in this case NH4 plus was considered as conjugate acid and my weak base was ammonia. Let us now try to convert this equation directly over here. What will this work out as? The pKb over here, the Kb was for this fellow here. So we could write that in this case, let's look at how this can be converted directly over here. If I am considering ammonium ion as the weak acid, then ammonia works like the conjugate base over there, correct? So I can write in this scenario here Ka for NH4 plus, this is already known, I'm just mentioning it, is equal to Kw by Kb of ammonia. I can substitute for anything over here. I can substitute for this Kb of ammonia now. Let's say I'm substituting for Kb of ammonia from this over here. If I substitute this equation Kb of ammonia here, what will I be having? I'll have POH is equal to P of Kw by Ka of NH4 plus log of NH4 plus divided by ammonia, correct? So now I can take everything else to one side and I can take the OH to POH to this side, meaning I'll now have, let's say I'm bringing this fellow to this side and I'm taking this term and this one both to this side. Okay, I've written too big over there, so I'll just put a tiny arrow here and a tiny arrow here. Okay, so if you're going to be doing this, what will this equation now look like? It will look like pKw minus POH is going to be equal to, in this case I'll have all the other fellows on one side, so it will be so it will end up working out as, now in this case it was minus, because it is P of divided by in the denominator, so it will end up being negative over here. So if I take it to the other side, it will become positive. So it will become pKa of NH4 plus will effectively, if I'm putting it as plus, that is a problem. So let me put it as a minus because I have to take it to the other side. Minus log of NH4 plus by NH3. Now, if I'm now adjusting it as necessary, pKw minus pOH is pH. So it becomes pH is going to be equal to pKa of NH4 plus and it was minus log of NH4 plus by NH3, so make it plus, so it becomes plus log of NH3 by NH4 plus. As you can quite clearly see, this is going to be my Ka for weak acid, and this fellow will effectively become conjugate base, this fellow will be the weak acid. It works out as the same equation as earlier mathematically. You are clear with this part over here, how it all connects mathematically?
Yes, sir.
Okay, alright. So this is going to be the second type of buffer solution which you will be coming across in overall. So the first type of buffer solution was something where you had, where was that? Yes, first type of buffer solution was here where we had a random weak acid and a random weak base, where they were not related to each other, they were not connected with each other, and we had it. So we had that kind of a scenario there. Second type of buffer is this one, where we are having a relation between the two of the fellows there. Either the weak acid and its conjugate base or the weak base and its conjugate acid. Both technically, mathematically are the same, which is what we have discussed over here in the last few pages now. Now, the third type of buffer is same substance acts as weak acid and weak base from two different ends in the molecule. What is this one going to be an example of? This is going to be the case which we have already seen actually, where we are having HCO3 minus. If you are considering HCO3 minus over here, what is the idea behind HCO3 minus? We have two locations there. So we have one location which is capable of acting as conjugate base of Ka1, and this location is going to be weak acid Ka2. So we are having two separate locations in the same molecule, each being capable individually of behaving either like a weak acid or like a weak base or as similar to one of those over there. So this is also going to be by itself a buffer. So broadly speaking, there are three categories of buffers. One where there is only one general category of buffer, which is it has to contain something like a weak base and something like a weak acid. So if it should contain one of these two, you can have them being completely independent of each other, which is case 1, where you are having a random weak acid and a random weak base, or their salt. Second is when they are related to each other, where you are going to be having a weak acid plus its conjugate base or a weak base plus its conjugate acid, the related ones. Third is the same molecule, same substance, one substance only, but it can act as acid and a base, weak in both cases, from two different ends of the same molecule. As long as that is going to be the case, this is going to be the scenario here. We have already discussed pH of each of these kinds of things. So ultimately, so far what are the cases we have had a look through so far? We have had a look through finding pH of the following types of solutions. If there is a strong acid only, strong base only, mixture of strong acid plus strong base, weak acid only, weak base only, strong acid plus weak base combination, what happens in that particular case? Now, there are a few middle cases here which come up from titrations. I'll have a quick discussion on them also in the form of a few questions in a bit now. So we will start off with the two cases which we are going to be looking at now: strong acid plus weak base and strong base plus weak acid type of solutions. So if I'm looking at a strong acid plus weak base solution, what is going to be happening over here? In this case here, there are many different scenarios over here. So let's take a simple strong acid and a weak base and try to analyze over here. If I consider a strong acid and weak base here, what is this going to be? How do I look at the different cases here? So this means I can have HCl plus NH4OH or ammonia, whichever way you should call it. So if I'm going to be considering this over here, let's take this as C1, let's take this as C2. Case number 1 is going to be if C1 greater than C2. What will be happening there? In that case, C2 will be fully consumed, it will be the limiting reagent, it will be fully consumed, and I will have HCl left over plus NH4 plus Cl minus. This NH4 plus Cl minus is similar to a weak acid. So we have a strong acid plus something similar to a weak acid being the case over here, which effectively is going to be very straightforward in the sense you'll have only one of them dominating and the other one you can partially neglect over there, or you'll have to sit and solve a quadratic wherein you make sure the strong acid dissociates first. I'll just take an example and discuss it off. So let's say I'm having HCl which is 0.10 power minus 2 molar, and let's say I'm having CH3COOH which is going to be 10 power minus 3 molar. In this case, we can neglect H plus from CH3COH. Because that is going to be too low. Even if the CH3COH is going to be 10 power minus 2, same thing applies over there also, 10 power minus 2 or lesser. Similar amounts or lesser, you can neglect the H plus from CH3COH. Of course, one more data should be given is Ka is approximately equal to 2 into 10 power minus 5. Some information of that has to be given. Neglect the H plus from CH3COH, meaning my pH for this solution will straight away be 2, approximately 2. We can directly proceed on and finish off this. Why? Because alpha in this case is going to be very low, because there is a huge amount of H plus already. So we can neglect alpha completely from H plus concentration point of view also. pH becomes equal to 2. The other case over here is if I am having say 10 power minus 4 molar HCl plus 10 power minus 2 molar CH3COH. Same Ka value is given over here also. In this case, I can't neglect the H plus from the CH3COH here, because H plus from HCl is very low. So here what I have to do is I have to write the equation CH3COH is an equilibrium with CH3CO minus plus H plus. I will of course be having what is called as common ion effect, in the sense we are already having 10 power minus 4 molar H plus in the beginning, and this is 10 power minus 2. This guy was 0. So we have 10 power minus 2 minus X. This will become X. This will become 10 power minus 4 plus X. X though is going to be very small, but it is negligible compared to 10 power minus 2, but not negligible when compared to 10 power minus 4. Alright, it is negligible only compared to 10 power minus 2, not compared to 10 power minus 4 over here. So this part I can now approximately write it as 10 power minus 2. But this part here I cannot neglect it over here. I should not be removing it out, because the X value will be definitely in the same level as this, or greater or slightly lesser, which means it is comparable to it. So no neglecting it there. So what will I be having here as equilibrium constant? Ka here as usual. So what will I get the equation as? Ka works out as 10 power minus 4 plus X into X divided by 10 power minus 2. When you sit and solve this over here, you will be getting a value of X over here. This should be fairly straightforward. I think it is just 4 and 1, I suppose. Something like that. It should be fairly straightforward. X, I think X will come out as approximately 4 into 10 power minus 4 over here. I want you to try solving this quadratic here. If my assumptions are correct over here, I should be getting it like this. You should be quick at solving quadratics, right? Faster than me for sure.
Yes.
So solve this off, please. Are you getting something approximately here? This should work out like this. I am not sure. It should be somewhere around here. If my approximations are correct, it should be somewhere around here.
Yes, sir.
Approximately this. You've checked it now?
Yes, sir.
So if this is going to be the case here, then now you can see that this pH or the H plus concentration actually now works out as 5 into 10 power minus 4. It was not 10 power minus 4, it is 5 into 10 power minus 4 in total over here. So now your pH is of course going to be influenced by the CH3COH also. So when you're going to be having these two kind of solution available, strong acid plus a weak acid, this is how you proceed and solve for it. So this case is going to be strong acid plus something similar to weak acid present, which is going to be solvable in this fashion like this. Now let's look at the case 2 over here. If I am going to be having C2 greater than C1, what will happen in that case? HCl will be consumed. So I'll be having NH4OH left over. And NH4Cl produced. This of course is your buffer solution which we have seen earlier. So we can use buffer equation and directly find the pH or pOH of this particular thing depending on how you are applying the equation. If you put it as pKa plus log of conjugate base by weak acid, you will get pH. If you put it as pOH is equal to pKb plus log of conjugate acid by weak base, or in that fashion, you will of course be getting pOH. So depending on which one you want, decide which equation you wish to use over there. Or adjust as needed according to the question. After you have memorized one formula, convert as needed, no problem. So this is going to be a buffer solution. We have already learned how to find the pH of this solution also. The third case is going to be if I am having say strong acid HCl plus if I am going to be having weak base ammonia. So in this case here C1, C2, if C1 is equal to C2, what do I have? I have only NH4 plus Cl minus present. Again, this is going to be something where we have found out how to treat this over here. Treat this as a conjugate acid of weak base only implies you can have regular similar to weak acid equation. All those equations are going to be applicable and you can directly solve it off for this over here. Now, how will you be getting this question over here? You will get this in the form of titration. They will tell you something like say I am going to be having 50 ml of 0.1 molar HCl in beaker. Okay, we are going to be adding ammonia dropwise. Ammonium hydroxide 0.1 molar solution added dropwise. In that particular case, what is the idea here? If I am going to be having, let's make them into cases over here. Let's call it case 1. Case 1 is going to be when I am going to be having strong acid greater than weak base. This is going to be of course from 0 to 49 ml, both included. Second case is going to be strong acid is equal to weak base. This is going to be of course the case which we have just seen above over here. This is going to be the case where you are going to be having only 50 ml perfectly. Last one is of course going to be case 3 where you are going to be having weak base greater than strong acid. In that particular case, this is going to be your scenario where you are going to be having greater than, or the, let's make it 51 ml plus plus. That is going to be this scenario over here. It is inclusive of this 51 ml boundary here. So effectively, what is case 3? Case 3 is going to be, which one is that? This one is going to be case 3. And we will be having this one as case number 1. So this entire thing is case number 1. This is also case number 1. And this fellow is going to be case number 2. You're clear with this part over here, how this titration will go, depending on where you are going to be having how much volume of what is given, depending on the stoichiometry writing of it, you will have to basically decide over here. You want me to show you the stoichiometry part over here, or you are already clear with this when I give you the volumes itself?
No, I'm clear with it, sir.
Okay, alright. So this is going to be the case for this solution now. So which solutions are we now covered off with? We have now covered off a strong acid, strong base, strong acid plus strong base, strong acid plus weak base. Obviously, if I covered strong acid plus weak base, exact opposite applies for strong base plus weak acid. We have also covered weak acid plus weak base under the condition both of them are concentration C and C. What else have we covered? We have also covered strong acid plus weak acid in both cases if they are comparable, not comparable, comparable, strong acid plus weak acid excess. In that case, it's going to be solving. Same type of logic will again apply for the next ones there. If I have a strong base plus weak base, one will be the comparable case where you assume only the strong base produce OH minus and close this scenario there. Another is going to be strong base plus weak base where the weak base is present in excess. So the weak base in excess, just like the previous case, you have to sit and solve the quadratic. No other option is available out of that. Of course, what are the other cases? We have also covered the buffers there. We have covered salt of strong acid, strong base, which is going to be neutral because of spectator ion business there. We have also covered salt of strong acid, weak base, which is of course going to be something which is going to be conjugate acid left in solution. Conjugate acid only in solution. So this we will treat it like similar to weak acid. Of course, the next one was salt of strong base and weak acid. Again, in this particular case, we will take conjugate base only, similar to weak base. And we have also seen salt of weak acid, weak base, where you are going to be having both of them in equal concentration. If they can produce equal concentration, equal number of ions, then this particular logic will work. So this is a whole bunch of cases. We have also seen for middle salt of polybasic acids. Polyacids or bases. One of the things which we have not seen yet is polybasic acids and polyacidic bases. How to find out for that? So let's quickly close this particular acid base stuff off by discussing that off next year. So let's say I'm going to be having a polybasic acid. Let's take a simple one, H2A. So if I'm having H2A here, this fellow will basically be having H2A in equilibrium with H plus plus HA minus. This equilibrium constant will be called Ka1. Next up, I'll be having the HA minus can still behave as a weak acid and dissociate again. This time though, I'll be having it as Ka2 and I'll be having A minus 2 ion being produced over here. Always, what will be the case? Ka1 will always be greater than Ka2. If Ka2 is greater than Ka1, Ka2 will be called Ka1. That's all, nothing else. Alright, there is no way that is going to be ever happening. That is not a theoretic, that is just a random bullshit point. But the idea here is Ka1 is always greater than Ka2. Usually, it will not be just greater than, it will be much greater than Ka2 usually. Alright, so not just normally greater than, usually much greater. So, usually we can say Ka1 in comparison to it, we can neglect Ka2 comfortably. But let's try to do the standard equilibrium stuff and then figure out what to play it out with. So H2A is going to be in equilibrium with H plus plus HA minus 1. So let's say I start off with concentration of this guy as C. Then for this Ka1 I will have an alpha 1 and for Ka2 I will have an alpha 2. So I'm going to start off with concentration C. So what will I be having? I'll have this initially as 0, or rather let me just put the equilibrium concentrations directly, that will be more sensible over here. So at equilibrium this will effectively become C into 1 minus alpha 1, this will become C alpha 1, this will be C alpha 1. Now in the next equation what is going to be happening is we will be having HA minus is now going to be dissociating again into H plus plus A minus 2. So what happens is a little bit more H plus is produced over here. So what will now happen, I have C alpha 1 here at the beginning itself. This will also be C alpha 1 and it will be C alpha 1 into 1 minus alpha 2 here. Over here it becomes C alpha 1 into 1 plus alpha 2, which is also going to be what is present over here. At equilibrium now both locations it has to be the same thing. And the A minus 2 is an unknown in this particular case here. But what can we do here? We can say alpha 1 is much greater than alpha 2 always, for sure. If that is the case, I can write this as approximately equal to C alpha 1 and I can write this fellow as also approximately equal to C alpha 1. Because 1 minus alpha 1 and 1 plus C, 1 minus alpha 2 and 1 plus alpha 2 are both equal to 1. So what am I taking over here? I am taking 1 minus alpha 1, 1 minus alpha 2 is approximately equal to 1 and 1 plus alpha 2 is also approximately equal to 1. So both of those approximations if I am taking, I will be getting it like this. Meaning I can now write in this case over here K2, which is my equilibrium constant for this second equation, is going to be H plus into A minus 2 by HA minus. So it is H plus into A minus 2 by HA minus, meaning it is C alpha 1 into A minus 2 divided by C alpha 1. So both will cancel, meaning I will be having concentration of A minus 2 ion being equal to Ka2 when you are having this kind of a polybasic acid where there is a dibasic acid at play over here. So this is going to be one of those cases with respect to polybasic acids which you need to properly understand in this scenario over here. Okay, now this is going to be one of the types of polybasic acids. We can of course extend this kind of logic on and on and on. For instance, let's say I am taking a triple acid, H3A. What will I have? I'll have C1, no need to call it C1, C into 1 minus alpha 1, C into 1 minus alpha 1, H plus H2A minus 1. So I'll have this as C alpha 1, this will be C alpha 1, and this equilibrium constant will be Ka1. Next up, I will be having H2A minus in equilibrium with H plus HA minus 2. In this case, I will have this as C alpha 1 still, this will be C alpha 1, this will be, of course, we just derived this comes out as Ka2. Alright, this comes out as Ka2. Lastly, in this case here, of course, what else will I be having? I will have this as Ka2 over here. Third equation we will be having is the HA minus 2 will then be dissociating further to give me more H plus A minus 3. What do I have over here? This will still be C alpha 1. Nothing will change this. Alpha 1 is going to be much greater compared to alpha 2, which is going to be much greater compared to alpha 3. So we will say 1 minus alpha 1, 1 minus alpha 2, 1 plus alpha 2, 1 minus alpha 3 and 1 plus alpha 3. All of these are going to be approximately equal to 1. We can happily approximate that. So what will we be having next over here? Over here though, I will now be having a slight difference. This will be K2 here. This though is an unknown. Alright, this is going to be an unknown in this particular case here. How do I calculate this one over here? This will be Ka3 now, correct? So I can now write Ka3 is equal to H plus into A minus 3 divided by Ka2. Meaning we will now be having C alpha 1. So A minus 3 concentration works out as Ka3 into Ka2 divided by C alpha 1. How do I calculate C alpha 1? Very straightforward in these kind of polybasic acids. Alpha 1 is going to be approximately equal to square root of Ka1 by C. Of course, when Ka1 is less than 10 power minus 3. If Ka1 is less than 10 power minus 3, you can happily apply this. Same approximations, all approximations work. Meaning H plus concentration is equal to square root of Ka1 into C. And what will pH be? pH will be equal to half into pKa1 minus log C. So all of these equations will perfectly well apply. So you can substitute over here as you need to and solve for this. Meaning this A minus 3 concentration. What else can I write this as? Concentration of A minus 3 is going to be Ka2 into Ka3 divided by C alpha 1, which works out as nothing but square root of Ka1 into C. So this can be written as Ka2 into Ka3 divided by square root of Ka1 into C. This is concentration of A minus 3. When is this applicable? If Ka1 is less than 10 power minus 3. Under that condition, I will have this straight away holding good. Of course, if I want a polybasic acid with 4H plus being produced, same type of logic, extend it one more level. That's all. So you will end up having polyacidic bases being of course the exact complement of this. So same type of logic with respect to the bases there. Everything else you will be having the same. That is pH will become pOH, Ka will become Kb. That's all. Instead of Ka1 it will be Kb1, instead of Ka2 it will be Kb2, Ka3 ke badle mein it will be Kb3. That's all. So same kind of analysis, same logic. The conjugate bases over here will become conjugate acids over there. That's the other logic to apply there. You're clear with polybasic acids and polyacidic bases to an extent now?
Yes, sir.
Okay, alright. Next up, in this itself, there are some very interesting questions which can be made over here. For instance, they can give you a question like this. Let's say I'm going to be having a solution which contains, say, H3PO4, which is going to be, say, 1 mole, or 1 mole, fine. And let's say I'm going to be having, say, NaHPO4, Na2HPO4 being, say, 2 moles, and say NaH2PO4 being, say, 1 mole, and say Na3PO4 being, say, 2 moles. All of these are mixed into one solution. If I'm asked to find the pH of that solution, how do I proceed for this and how do I go for calculating this? So the idea here is you have to understand what are the different species at play over here. What are the species at play here? You have H3PO4, you have H2PO4 minus, you have HPO4 2 minus, and you have PO4 3 minus. So in this here, this fellow is the strongest base. Why is this the strongest base? Because this is conjugate base of Ka3 of H3PO4. So it is going to be the conjugate base of lowest Ka, meaning it will be the strongest among the 3 bases or whatever bases you are going to be having here. So which are the conjugate bases? These 3 are the conjugate bases. And these 3 are going to be my acids over here. So among the acids, which is strongest? H3PO4 is strongest among the 3. And of course, this is the strongest base in solution. If I am going to be having it like this, now I can now straight away proceed and understand that if I have a solution, let's say I am looking at a solution now, a different type of a solution containing 2 acids. Weak acid 1 and weak acid 2. I am adding a strong base to this. The strong base will react with which acid first? Is there a preference at all?
No, sir.
There is a preference because everything is mathematical, everything is equilibrium. So there will be a clear-cut preference. The strong base reacts with stronger out of the 2 weak acids. That is why your Ka actually comes into play. So if you are going to be having Ka for one of them being substantially higher, by say even 100 times or even 10 times, that will react much more. Because the rate is going to be depending on the amount that get dissociates, but it also depends on how good it is going to be at reacting also. So even 10 times more Ka will basically translate into nearly full completion of that reaction before this second fellow even starts reacting. Only when they are of very much comparable level, not even 10 times, but within like say 2 or 3 or 4 times, then you will have both of them reacting slightly equally or relatively equally. Even then, the one which is stronger will react to a much greater extent. It will react to how many ever times it is going to be better, multiple times of that it will end up reacting. So you will end up having strong base reacts with stronger out of the weak acid 1 and weak acid 2 preferentially, not fully, preferentially. Preferentially means to a good enough extent. So when you are going to be having these 4 now present in solution, let us now put down each of them what is actually the amounts each of them are present. So we have H3PO4, H2PO4 minus 1, HPO4 2 minus, and PO4 3 minus. So each of them different amounts were there. So let me just put down them. So 1, 1, 2, 2. This and this were given oppositely. So this is 1, this is 1. The last 2 are 2, 2. So we have 1, 1, 2, 2. So what will be happening? Strongest will react first. So these 2 buggers will react. When these 2 react, this will be the limiting reagent. This will become 0. This will become 1. But at the same time, it doesn't stop here. This also increases in this reaction because this fellow is reacting as a base now. It will produce its conjugate acid. This one's conjugate acid is going to be HPO4 2 minus. So this will increase by 1 and become 3. This fellow will increase by 1 and become 2. Why? Because the H3PO4 would have produced this over here plus 1, and we'll end up having this fellow increasing and adding a plus 1 for this one over here. That is the idea over here. Next up, this is the current scenario now. Now which is going to be reacting, this is my strongest over here and this is my strongest over here. Limiting reagent is this 1 here, so this will become a 0, this will become 1. Again, this will produce a plus 1 on this side, this will also produce a plus 1 on this side over here. Thereby, this fellow will finally become 3 plus 1 plus 1, it will become 5. So what is my final solution containing? So final solution contains two things right now. What does it contain? It contains H2PO4 minus over here, and it contains HPO4 2 minus. This is 5 millimoles, this is 1 millimole in the same solution, or 5 moles, 1 mole in the same solution. Obviously, now we can treat this as an acidic buffer, where I can say this is my weak acid Ka2, this becomes conjugate base of Ka2. Right? I can call it that way. In which case, this can be now treated like a buffer solution. If it can be treated like a buffer solution, I'll have pH of the solution being equal to pKa2 plus log of conjugate base by weak acid, which works out as 5 by 1. So it becomes very straightforward to solve, and you can straight away proceed and solve this case off very comfortably. You will not get this kind of a complicated thing usually unless and until it is a good JEE advanced kind of paper where they have given you clear distinction between Ka1, Ka2 and Ka3. They should not be close enough by. If they are close enough by, they will not react nearly completely. Each of them should be 100 times each other at least. So Ka1 should be more than 100 times Ka2, Ka2 should be more than 100 times Ka3, and Ka1 should be less than 10 power minus 3. You understand those cases now as to what I mean individualistically?
Yes, sir.
So you will have this in a very good paper. You will not get this kind of scenario in an easy paper, but this is one of those kind of cases where polyacidic bases and polybasic acids can be combined with each other, and many different kinds of interesting questions can be made. Now, the next bit which is there in this chapter is of course going to be solubility product. What is the idea behind solubility product? If I am going to be having, say, something which is going to be a salt, which is an ionic salt. This is meant for ionic salts. It is not meant for random salts. It is meant for ionic salts. Ionic salt, now what does it mean? Part which dissolves. We will be assuming it dissociates fully. Or we should have one more equilibrium associated over there. So we will be assuming that the part which dissolves dissociates completely when it comes to these kind of cases. So what is the idea over here? We are now going to be taking some random kind of a salt, like say barium sulfate. We know this is highly insoluble. So what happens? This is an ionic salt also. Barium hydroxide is a very strong base. Sulfuric acid is a very strong acid. So the salt of this should be perfectly ionic, meaning whatever part dissolves should dissociate completely in solution. So this will effectively become barium 2 plus sulfate ion. So if I am going to be having this as the equilibrium over here, this is a solid. It is not going to be dissolving much, only a tiny bit dissolves. That tiny bit which dissolves completely dissociates. So effectively speaking, what is the equation which we are writing? We are writing it like this: BaSO4 solid originally becomes BaSO4 aqueous. Then that becomes Ba2 plus, or rather we can say this is now going to dissociate completely. It becomes Ba2 plus SO4 2 minus. So this, whatever amount has dissolved, let's say the amount which dissolved was concentration C. This should have been 0, 0 at start, but this will dissociate completely to become 0. These two will become C and C. So effectively speaking, instead of calling it C here, we will call it S. Because solubility is going to be something which is what we are looking at over here. So we'll use a new term S, which is going to be defined as solubility of salt in moles per liter. Okay, it is going to be moles per liter over here. That means moles of that salt which have dissolved in 1 liter of solution. That is what we are going to be taking. So in the case of barium sulfate here, this is a solid. Solid means concentration is constant. Why? Because it is going to be having a standard density which is not going to be changing. Surface area will matter, but if it's powdered, activity will be different. We will be calling it as activity in that particular case. We will not call it density, but either way it is going to be a constant. So what will we be having over here? This equilibrium constant, K equilibrium here, is going to be nothing but barium 2 plus into sulfate. Of course, we will be having into concentration of the solid over here on the reactant side, on the other side over here. If I combine these two here together, we will end up calling that as K solubility product. This is meant for partially soluble or insoluble salts, ionic salts. This works out as S into S. We will be having it as S squared. This is for a salt which is going to be like say barium sulfate or calcium carbonate or NaCl or KCl, anything where we are going to be having S and S being generated, we will have this perfectly applicable. Let's look at another salt now. If I am going to be considering a salt like say Na2SO4, this fellow is going to be technically in a solid form. It will be still in equilibrium with 2 Na plus SO4 2 minus ions. If S moles dissolved, that means 2S moles of Na plus are formed and S moles of sulfate ion are formed, meaning my KSP expression here works out as Na plus whole squared into sulfate. So it works out as 4S squared into S, which works out as 4S cubed in this particular case here. Next up, we can have many different types of salts like this, of course. We'll have different variations, of course, available. Let's say we are going to be having Na3PO4. In this case here, what will we be having? We'll have the KSP expression working out as 3S whole cubed multiplied by S. So it works out as 27S power 4. Why? Because this will be Na plus whole power 3 into PO4 3 minus ion concentration, which works out like this. If I have say Al2SO4 thrice, in this particular case we end up having KSP working out as aluminium 3 plus squared into sulfate ion cubed, meaning we'll have 2S whole power 2 into 3S whole power 3. So it works out as 27S power 3 into 4S power 2. So it works out as 108S power 5. So these are general expressions to understand the KSP aspect of things over here. Now in the chemical equilibrium part there, we discussed something called as reaction quotient. This comes out to be very useful for us in terms of understanding this solubility product over here meaningfully. So reaction quotient, we can now define it with respect to the solubility product here, QSP over here. So this is going to be something which is just product of ions, not at saturation, not necessarily at saturation. So how to understand this, how to proceed for this part over here. So if it is going to be nothing but product of the ions but not necessarily at saturation over here, we can say if QSP is going to be equal to KSP, that means the solution is a saturated solution. What does that mean? Any tiny bit we add now will immediately precipitate only, it is not going to be dissolving any further. If QSP is less than KSP, what that tells you is we are going to be having a dilute solution, meaning fully dissolved, and little more can dissolve. Effectively, forward direction of solubility is going, implies forward direction of solubility reaction. Solubility reaction, not dissolving reaction, the reaction which I have written down over here. Forward direction of this fellow is going on, because Ksp is equilibrium constant for this. So if I have the Q, the product multiplication over here being less than the Ksp, more of forward will happen, more of product is produced, more of it will dissolve. So it is not yet fully saturated, it is a dilute solution, more can dissolve, and yeah, it is fully in solution. Lastly, if we end up having QSP working out as greater than KSP, what does that mean? Implies backward direction of dissolving happens. What does this basically mean? This means precipitation of salt happens. Till when? Till QSP becomes equal to KSP. This is effectively what is going to be happening in this kind of a scenario here. So you are going to be having many different cases associated with this over here, where you have to understand many different models of questions. We will discuss a few models of questions also, but I'll describe the few models first over here. When I'm discussing questions, solubility product method, there are some good number of questions. So right now though, I'll probably not discuss questions today. So I'll just discuss some of the standard models which can appear over here. One kind of model which will appear here is like this. Let's say I'm having a solution of HCl, which is going to be say 10 power minus 2 molar. Okay, let's say I'm going to be giving you barium chloride is going to be having solubility KSP, not KSP, let's say solubility of barium chloride in pure water. I'll give you barium chloride solubility in pure water is going to be given as say 10 power minus 2 moles per liter. Okay, I am asking find solubility of BaCl2 in 10 power minus 2 molar HCl solution. If this is the question, how to proceed over that? They are given solubility of barium chloride in pure water as 10 power minus 2 moles per liter. This can be given as grams per liter also. Alright, if they are giving it in grams per liter, it is going to be irritating. You have to sit and solve, convert it into moles per liter, and then find KSP and then proceed. If it is given in moles per liter, like in this easy nice case over here, we can proceed on much more easier. So barium chloride will basically be solid in equilibrium with barium 2 plus 2Cl minus. These two fellows will be aqueous. This is solubility S, this will be 2S, meaning we will end up having, in this particular case here, KSP works out as what? KSP works out as 4S cubed. They have given us solubility as 10 power minus 2 moles per liter, meaning we end up having KSP of barium chloride working out as 4 into 10 power minus 6 S cubed. So 4 into 10 power minus 6. Now next up, they are asking us what is the solubility of barium chloride in a solution which is already having HCl. So if I am looking at barium chloride solid again, this time I need to now write barium 2 plus 2Cl minus again. But in this case, my starting Cl minus is at start. I have from HCl 10 power minus 2 molar already present. So I will have this as 10 power minus 2 from start. Where is this present? From HCl. Already present. So what will I now be having over here? Now I will be having this as 10 power minus 2 now. I will now have solubility, let's call it as S1 now. Or rather some X over here. In this, or yeah, X will take. So if solubility is X now, then this would have been 0 in the beginning. So this will become X, this will become 10 power minus 2 plus X. What is this KSP over here? This KSP we calculated over there as 4 into 10 power minus 6. So effectively what do we end up having? We end up having in this particular case here 4 into 10 power minus 6 being equal to X into 10 power minus 2 plus X. Now simple way of solving, approximate and see if you can neglect something. But if you are neglecting something, after you get the solution, you have to fit it back and check if it is acceptable or not. So in this case here, I am going to write 10 power minus 2 plus x as approximately equal to 10 power minus 2 and solve and see. So solving and seeing, we get 4 into 10 power minus 6 is equal to x into 10 power minus 2, implies x works out as 4 into 10 power minus 4. Substitute that back and check. 10 power minus 2 plus 4 into 10 power minus 4 is approximately equal to 10 power minus 2. Acceptable. It is not that bad of an approximation. It is still an approximation, yes, but not too shabby. So accepted. No real problems with respect to that. So this is going to be your case over here. So this is going to be the new solubility of barium chloride in moles per liter still, in 10 power minus 2 molar HCl solution. Now, this is going to be sometimes asked in grams per liter again. So this thing, currently it is in moles per liter. Sometimes you might have to convert it into grams per liter for a particular question. If it is to be converted into grams per liter, what should you do? Of course, multiply it by molecular mass. Sometimes they might ask you to convert it into grams per some particular 1000 liters or 10,000 liters or whatever container it is or something of that sort. That also can be a question which is going to be a model out of this. So that is going to be one set of models which can come. Of course, you can have some straightforward questions. They will tell you this many grams of this salt dissolves in this particular scenario here in this solution. Find its solubility product. That is also another standard question. So in this particular case here, what is happening here? What is happening is, you can see that the solubility in this case is 4 into 10 power minus 4 when HCl is present. Whereas originally the solubility was 10 power minus 2. But when there is HCl present, it becomes 4 into 10 power minus 4. So in this case here, what did we have? With the HCl, we had it as 4 into 10 power minus 4. This is very, very small compared to the 10 power minus 2. Why is this the case? Common ion effect. What is the common ion effect here? Effectively, there is a product already present here. Because a product is present, less of the forward direction happens as you are going to be having a product already present. Which principle is this? Le Chatelier's principle. So if you are applying Le Chatelier's principle here, because one of the products is already present in the reaction mixture, the forward direction of the reaction does not happen so much. It happens to a much smaller extent than it happened when it was in pure water. Now, the same gimmick can be played in many different ways. They can give you a question where they are giving you mixing two different solutions. Say for instance, let's say I'm going to be having a barium chloride solution. Let's assume it is highly soluble. Actually, barium chloride is highly soluble. In the previous question, for the sake of a question, I gave you that. So let's say barium chloride solution is taken. Say concentration is say 10 power minus 2 moles per liter. And let's say sodium sulfate solution is taken. Let's say this is going to be say 10 power minus 3 moles per liter. They will ask you something like this. They will give you KSP of barium sulfate. They will ask you, if I mix these two solutions, some different volumes they will give you, if I mix the two of them, will I get a precipitate of barium sulfate? Yes or no? How do you proceed there? You will have to sit and calculate each fellow's concentration individually. Which two fellows? Barium 2 plus and sulfate ion concentration individually in the final solution, and then see if QSP of BaSO4 in final solution is greater than KSP of BaSO4. If it is greater than that, then precipitation happens. If it is lesser than that, precipitation does not happen. As simple as that. So you're going to be having these as the standard types of easy questions which you can get from this. Easy questions now, what I mean is JEE mains level questions. JEE advanced also, bulk of it will come under this kind only, but with one extra trick. In that common ion part over there, in the question which I gave you over here, I gave you chloride as the common ion because that was much more easier for us to proceed on with, much more easier for me to mentally give a question and then show you how to solve it. So I picked something very blunt over here. Of course, you can have it in a much more complicated way, where you can have say a complex being formed, or you can have say the buffer solution which is going to be maintaining H plus and OH minus concentration. that is going to be involved as a common ion in something. Like for instance, let's say I'm looking at solubility of, say, aluminium hydroxide. So if I'm considering solubility of aluminium hydroxide, this is going to be something which is again going to be dependent on what is the solution actually going to be. If it is already having a lot of OH minus, it may not dissolve so much. But if it can do some complexation there, it might dissolve also. So sometimes they will give you complexing side and they will give you another side where it is going to be behaving in a manner where there is common ion effect also. So ultimately the game is going to be to look at the question carefully, apply the same ionic equilibrium concepts which you have learned there, combine it with whatever QSP and KSP terminologies which you have to use, manipulate mathematically and proceed. So those are going to be the main types of cases. Of course, in terms of solubility product, there are much more interesting cases which can come up, especially when it comes to salt analysis based questions. I'll give you an example here. In qualitative analysis, salt analysis, you have not done this chapter, I think. You have not done this, na? Have you covered salt analysis, practical salt analysis in school? Not yet, right?
Not yet, sir.
Not yet, okay. So when it is going to be based on this over here, how to proceed and check out for this one over here, qualitative analysis part here. This is going to be something I suppose we'll discuss later. There will be a lot of common ion effect over here, along with solubility product, along with buffer solutions. So some very interesting questions can be made out of this theoretically. They are of course not going to be that straightforward. So when we come across some questions, if you have done a whole bunch of questions in your examinations, internal exams, Narayana, China campus there, the main top campus there, they will definitely have a good number of questions. Any of those questions, if you are not particularly keen on trying out, you want me to anyway show you how to proceed over there, send me the question. I will probably solve it and dump it online, or solve it and discuss it with you in the next session or whatever it is. So that is basically it from ionic equilibrium perspective. We are more or less done with the ionic equilibrium bits over here. There is one more part to discuss, which is going to be indicators. I am not sure if indicators is still going to be done or not in your syllabus. At least from a JEE mains perspective, it is definitely not there. JEE advanced perspective, I don't know. Indicators are usually going to be weak acids or weak bases. With one key difference there, if it is a weak acid type indicator, what will happen is weak acid and conjugate base are going to be present simultaneously. The key thing is weak acid should have a color 1 and weak base should have a color number 2. They should both be of different colors. That is the idea there. So weak acid and its conjugate base, if they are of different colors, then yes, usually it works as an indicator. Same logic applies in the opposite direction also if it is a weak base type indicator. You will be having weak base and conjugate acid. Again, this will be color 1 and this should be color 2. Both should be proper different colors, then it will work nicely. One of the most common weak acid type indicators is phenolphthalein. Phenolphthalein, I usually prefer abbreviating it as HPH. This is a weak acid type indicator. And one of the common weak base type indicators is methyl orange. I generally prefer abbreviating it as MEOR. So these are the standard fellows over here. Obviously, because it is a weak acid type of indicator, this fellow's range, the phenolphthalene's range is going to be 8 to 10. And earlier we used to sit and look at how to calculate range and all of that. That all used to be part of CBSE. But they removed that in one of the CBSE years. So it stopped showing up in JEE mains. This fellow's range is 3 to 5. Have you discussed this in your school, or you have not discussed indicator range calculation and all?
No, sir, they haven't discussed.
You haven't discussed. Okay, maybe some other time when we are pushing things a little bit more, we will go there. When we are seeing questions, we will see this. Or I'll give you a couple of questions on this and we'll discuss it based on those questions. From a more or less JEE perspective,